Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar. Where is AI digital infrastructure headed? My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past and present. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Schneider Electric. Schneider Electric's purpose is to empower all to make the most of their energy and resources, bridging progress and sustainability for all. They call this Life is On, and their mission is to be your digital partner for sustainability and efficiency. Schneider Electric drive digital transformation by integrating world-leading process and energy technologies, endpoint to cloud connecting products, controls, software and services across the entire life cycle, enabling integrated company management for homes, buildings, data centers, infrastructure and industries. Schneider Electric are the most local of global companies and are advocates of open standards and partnership ecosystems that are passionate about their shared meaningful purpose, inclusive and empowered values. Now today we will hear from our two speakers followed by our live audience Q&A. So I encourage you all to please send your questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Mark DeGara, General Manager for Data Centers from Schneider Electric. Mark oversees the growth and development of the cloud and service providers segment at Schneider Electric, including data centers for co-location organizations, internet giants, and telecommunication providers in the Pacific region. With over 25 years of experience in the IT and communications industry, Mark brings a unique ability to take the complex and deliver results-focused outcomes for customers. Please join me in welcoming Mark DeGara.
Thanks for the introduction. Good afternoon, everyone. So, how is AI driving infrastructure in the data center from the core to the edge? Really looking at how AI is going to impact the data center today and in tomorrow and what we're seeing. So, interesting enough, the pace of digital adoption and electrification is accelerating. So if we look at generative AI, it has taken 2 months to get 100 million users, whereas the World Wide Web took 7 years. So it's an amazing acceleration in terms of what's happening in terms of the use of the internet and ultimately where that is sourced from and ultimately sourced in data centers. But at the same time, we have electricity production. We're electrifying the world. So everything is moving to being the use of electric power. So you can see there that the consumption from 2000 out to 2050 is going to accelerate dramatically. And that is having an impact on where data centers are going to be located. Do we have available power for data centers, both here in Australia and globally, of course? Interesting enough, 3 billion more people are going to need access to electricity. So it is going to have a significant impact on the grid itself and as we electrify. So from a data center perspective, it's the new digital economy. The new digital economy is impossible without data. We all have mobile phones, we have tablets, we take photos on our phones, we're streaming, we're interacting, we're having live movies, we're having video conferencing. Good example is obviously the video conference we're having right at this point in time. So 90% of the internet users in 2030. So 90% of the world's population will be using the internet by 2030. So that's 7.5 billion people. So you think about that, 7.5 billion people using the internet and the amount of data that's generating and the amount of compute. 61% big data growth, over 100 billion IoT devices. And in terms of generating, the market, $16 trillion from AI. So ultimately, AI and the internet and technology is driving data. And ultimately, where does data live? It lives in data centers, whether that's core data centers, hyperscale data centers, or ultimately the edge. So we see it as the next industrial revolution. In my first slide, I spoke about 100 million chat GPT users in the first 2 months. Now, there's $1.3 trillion of generative AI market cap and a $60 billion yearly investment in AI by private equity firms. So there's a significant amount of money globally and here in Australia that is actually going into data centers. If I look at the market and what's in it, the news at the moment, we're talking about various companies investing, a 450 megawatt data center, a 300 megawatt data center, another 350. There's a huge demand for data centers to be developed and built here in Australia, and ultimately what impact that is having, and how AI is going to impact what is happening within those physical facilities. So, at the core, if we actually look at AI and what it is, fundamentally, AI is really algorithms sitting on high performance compute. But if you look at AI, there's the development aspect of it and the deployment of it. So you have large language models that is being developed. So they're developed in the core data centers. Ultimately, you develop your model and then it gets deployed. Now, the question of where it's deployed, is it deployed within the large data center? Is it deployed out at the edge? And the question is, where is that data being kept? If it's at the data center, latency is not so much of an issue. If it's a deployment is actually where the source of the data is, and I'll use self-driving cars as a good example, do we need the deployment near self-driving cars? Therefore, latency is an issue. Therefore, how do we then deploy out to the edge? And it all has an interaction. So there's the large core data center, there's the regional, and ultimately there's the local impact of what AI is doing and AI compute. So AI deployment brings its own challenges in the data center market. Capacity, the need for power. We saw on that first slide the growth in the requirement for energy, not just driven by data centers, but driven by electrification and the growth of the human population. Vacancy, all-time high. Is there a space available in data centers? Do we need to build new ones to be able to populate them? Rental rates in data centers are going up. And the big challenge is the design. How do we design for AI? As a consulting industry or consulting fraternity that we sit in with Engineers Australia, we as engineers, how do we design for them? How do we design for a data center today? How do we design for a data center tomorrow? And then how do we design for one in 5 years' time? So what are we building today? Is it going to be suitable? If I look back 10 years ago, yes, you'd build a data center and it was suitable for the next 5 or 10 years. We're seeing challenges now that data centers potentially are not even suitable for 6 months' time, let alone today. So that is one of the big challenges facing the industry. So the acceleration of data centers, we look at the growth. So if we look today in 2025, around 13%. If we look out to 2030, that's going to grow to 30% and beyond. But interesting enough, it's not just about AI. If you look at the underlying growth, it is still very much around cloud computing. So the majority of data centers is still being driven by cloud computing. However, we're going to see an extra 150 gigawatts. So think about that, 150 gigawatts of extra capacity added in the next 5 years. Now that power's got to come from somewhere, but also you've got to design the data center for it. 60% of the new builds will be allocated to AI. An average density of racks is going to be 40 to 100 kilowatts. Now we talk about 100 kilowatts, and I'll talk a little bit about more where the projection is. So NVIDIA earlier this year announced, seeing a 1 gigawatt rack. I saw Google 2 weeks ago announce that, okay, a 1 gigawatt rack is here. You think about 1 gigawatt, that is a significant amount, 1 megawatt in a rack. If I look at that and say that is a lot of power in one rack. So when I started, sort of 20, 25 years ago, we were talking about, 1 or 200 watts per square meter, maybe 300 or 400 watts in a rack. Now we're talking a megawatt. So a megawatt potentially in a rack. So that has a huge impact on how we design for that, both from a cooling aspect and a power aspect. So to thrive in the new era of data centers, we need to. I spoke about the increase in power. So optimize power capacity and efficiency, deploy high density infrastructure. So we are talking about, a megawatt a rack or 2 megawatts a rack. But let's say it wasn't even that. We're talking about 100 kilowatts a rack today. We're starting to see that deployed on large scale today. So 100 kilowatts a rack is high density, and we're seeing that deployed today. And how is that being impacted? Enhanced sustainability practice. So whilst we're deploying this high density infrastructure, the question then is, enhanced sustainability practices. We need to consider the sustainability impact of what we're doing, both today and long term. So in the forefront of what we're designing is, how is that going to have an impact on sustainability? So they're all intertwined. You can't have one without the other, and they need to be all considered. So, welcome to the new era of data centers. So, what's special? What's so special about an AI data center or a high performance compute data center? Rapid compute evolutions. I just recently spoke about, capacities going from 10 kilowatts a rack, 100 kilowatts a rack, 150, a megawatt, potentially 2 megawatts a rack. That's significant, and it's happening within a 6 month, 12-month, 18-month period. It's not happening in 5 years. Ultra power density, the density in a very small footprint. So if we talk about a conventional rack, 600 or 800 wide by 1200 deep, and thinking that we're going to fit a megawatt into that, or maybe two, 1200 amps a phase, 1500 amps a phase, that is considerable. And how do we reject that heat? How do we get that heat out? The other thing is the race to AI leadership. Certainly NVIDIA has captured the market, but we are seeing AMD, and I'm sure Intel as well, will come back into the fold. So who is going to win that leadership? Now, that's from a chip perspective. But then there's the question of who's going to win the AI race in terms of the algorithms and deployment of AI. Your Microsoft, your AWSs, and obviously companies that develop that as well. Then there's the dynamic profile. So the dynamic profile, it's interesting enough, if you look at a high performance compute, and we take the NVIDIA product, for example, it's peaking at anywhere up to 1.8 times its nominal power rating. So if we said it was a kilowatt, it's peaking at 1.8 kilowatts. So if you take that into design, what do I design for? Do I design for the 1? Do I design for the 1.8? What impact on UPSs does that have? What impact on cooling? If I was running on diesel generators, can a diesel generator take that overload in a short period of time? So that is another impact that has to be considered. And last, but certainly not least, is the architecture variability. And this is probably the biggest challenge we're facing in the industry today, is the ever-changing dynamic. Not so much from the core external infrastructure. So if I look at the MV feeding the site or the power articulation of the site, other than the larger capacity, 400 megawatt data centers, it's really impacting the white space. So what is happening at the rack? How do I get cooling to that rack? How do I get power to that rack? And how do I reticulate power? Is it AC fed? Is it DC fed? Is it liquid cooling? Is it air cooling? So energy strategy for the era. Interesting enough, if we look at the data center in whole, how do we get power to the data center? There's prime power, so that's obviously coming from the grid. Backup power, is that diesel generators? Is it BESS? And then last, but certainly not least, is available power. Do we have enough power at the grid to connect? So I'm building let's say, a 500 megawatt data center for this discussion. Is there the transmission lines available where I'm looking to build it? Does the network have that available? Do I want to put backup power on site? Is it diesel generators? Is it some alternative technology? And the other question then is, how do I manage the sustainability aspects of that? Do I use power purchasing agreements to buy renewables? And when I look at renewables, am I 24/7? So if we look at that, it's around energy procurement, on-site power generation, backup, battery backup and sources. And also, how do I manage those power sources? Do I control them on site, or does my network provider do that as well? So it's not just about more power, it's about optimized power as well. So it is strategic energy sourcing, monitor the market demands. Am I paying for power at a peak rate? Can I get it at a lower rate? Can I get renewables? Do I do on-site generation? Certainly in the US, we're starting to see this a lot more, where organizations are moving to gas turbines on site. Then the utilities go, well, hang on a minute, I'm the power generator. Do I take over that asset and do I work on it? And then ultimately managing the power sources. If I really want to go to 24 by 7 renewables, where is that power coming from? Is it coming from a hydro facility? Is it coming from a wind farm? Is it coming from a solar power? Is it coming from geothermals? Is it coming from a BESS? How do I manage that? Certainly, from a Schneider perspective, we help organisations around leveraging power and flexible power, but that's something to consider. So the data center itself is no longer just a consumer of power, but it is very much interacting with the grid and where that power is coming from. So end to end for AI, if we're looking at data centers, it has to be sustainable. And how do we design for that? AI ready for high performance powertrains. Hybrid and high efficiency cooling is very much a hybrid, and I'll talk a little bit more about that. And certainly Miguel, after me, will talk in a lot more detail about the cooling and AI. And last but certainly not least, safeguard your operations. When you're building this data center, you're looking about what do I do today? What do I do tomorrow? And then how do I safeguard that? How do I ensure that that data center is going to be suitable for the long term? And also from a sustainability perspective. And an operational perspective, yes, you can build the data center, but you have to operate it as well. And making sure you have the people, the resources to know the technology and also operate it. So, where does it all start? It starts with the GPU. If I look today, or actually, if I look back, we used to sort of build from the outside in. We used to go, okay, we're going to build a 5 megawatt data center or a 1 megawatt data center. And we go, yes, we need MV, we need transformers, we need MV switchgear, we need UPSs, etc. And we were going, okay, well, we'll have 1 or 2 kilowatts a rack, and we'll design for that. It's actually flipped. So today, it's very much starting with the GPU. So what is happening in the GPU? I'm using NVIDIA here as an example, but if we looked at a reference design that we built on about 18 months ago, we came out with a reference design that was designed for 70 kilowatts a rack. Now, we released another reference design only 12 months later, so around 3 months ago, at 132 kilowatts a rack. And this has been driven by the GPU. This has been driven by what's happening, in this case, NVIDIA, driving what's happening at the server level and ultimately what happens at the rack level. So, yes, we released a reference design of 132 kilowatts a rack. Our good friend Jensen then comes out earlier this year and goes, oh, hang on a minute, we're going to go 200 kilowatts a rack. Oh, no, actually, we're going to go to a megawatt a rack. And as I said, we saw Google about 2 weeks ago release a megawatt deployment around a rack. So our reference design's ability to keep pace is a challenge for all of us. And those architectures are not necessarily, those reference designs aren't necessarily telling you how to do it. It's invoking thought on what are the things you need to consider when you are looking at high density compute and ultimately AI computing. So then if we look at the data center itself, certainly from a Schneider perspective, we talk about grid to chip and chip to chiller. And it's very much looking at the whole data center. We talk about switchgear. What impact is AI having on the switchgear? Low voltage and medium voltage switchgear. High performance functionality. I spoke about the dynamics of, potentially peaking at 1.8 times what the nominal load is. How does that flow from there into the input? We then look at UPSs. If we look today and sustainability is a key aspect, our UPSs are getting smaller, but how do those UPSs handle those AI profiles? Can they handle those 1.8 peaks? Will they go onto battery? And a discussion for another day is what sort of energy storage is being used in those UPSs, lithium batteries. And there's a lot of talk about, different chemistries, but ultimately they're still lithium batteries. And there's a lot of discussion around that. High power final distribution. That is where we're really seeing a change. 40 kilowatt racks. Okay, we could have a power rail, 60 amps a phase, 100 amps a phase. Now we're talking maybe 1,000 amps and beyond, 1,000 amps per phase. So what does that look like in terms of a power rail? Is there even a power rail available today for that? Certainly at 1,000 amps a phase, no. Busway is available, but certainly at a rack level, 1,000 amps a phase is being used with multiple power rails. So you'll have, 3 or 4 power rails into the rack. The other really interesting is racks and containment. To give you an idea, a high performance compute rack today is 1,800 kilos and beyond. You think about that, 1.8 tons sitting in a fairly small footprint, nominally, 800 mil by 1,200 mil. Considering that, how do I account for that? Now, if I'm building a new data center and I can load my floors for it, 1.8 tons, yes, I can work with it. But if I'm in an existing facility and I have multiple stories and I'm going to deploy 10, 15, 20, 30 of these 1.8 ton racks, can my existing floor take it? Can my goods lifts take it? How do I deploy that? So we talk about grid to chip. The reason we talk about that is there's an impact on all aspects of the data center. So I hear a lot of people talking about, oh, we're looking at what's happening at the rack level. Absolutely, we need to. But then what a flow-on effect does that have upstream? If I'm using bus bars to connect the racks, do I need a 400 amp bus bar? Do I need a 1,000 amp? Do I need 2,000? Then how does that fly out the MV? And if you look at this picture, which is interesting enough, you'll see the data center there, the grey space, so to speak, and you'll see the infrastructure, generators, chillers, etc. on the outside. New AI data centers potentially are 25% less footprint for the white space. And if we even go to 2 megawatts a rack, potentially even lower. However, the infrastructure to support it hasn't really changed. So traditionally, a lot of people will put, generators and chiller plant on the roof. Now, if my data center has a smaller footprint, can I fit the generators and the chillers on that roof anymore? If I have the weights we're talking about, does it limit the amount of stories that I have? Do I have 1 story? Do I have 2 stories? So it has a whole impact. So I spoke about the UPS and one little product push. Certainly this presentation's about thought leadership and not product presentations, but I'll focus on the UPS just a little bit. We've released our new Galaxy VXL, so the GVXL. It's 52% smaller than the industry average. Now, the advantage of that is the sustainability aspect. The other thing is with the sheer dynamics of what's happening in the data center, the ability to modular, the ability to be able to support larger loads is considerable. The other big one is from a footprint perspective. We saw the data centers getting a lot smaller in terms of the white space, but this helps in terms of the infrastructure. And it has the flow-on benefits from a sustainability perspective of the fact that your transport costs are down, your cabling costs are down. Interesting enough, this is 1.2 meters wide and it is 1.2 megawatts. Now we're starting to hit the limitation actually of how you can get cables in and out of this unit. So I spoke about the 1 megawatt rack. If you think about the 1 megawatt UPS at 1200 wide, you talk about the 1 megawatt rack at 600 wide, the same challenges of getting cables in and out start to occur. So this is our new GVXL. I'll stop talking about that and move on. So then we move to the cooling side. So we spoke about grid to chip, so taking power from the grid down to the chip. Now at the chip level is where we're generating the heat. So now we talk about chip to chiller. So it's about taking that heat and removing it. So if we start to look once again more broadly at the data center, we talk about liquid cooling and liquid distribution. So there's liquid to liquid cooling distributed units. There's liquid to air. There's high temperature chillers. So what we've seen over the last 5 to 10 years is a real increase in what temperatures are coming off the compute. Therefore, if we can drive temperatures up into the chilled water, ultimately that means we can actually have a lot more free cooling. So if we're running, a 20 to 30 degree chiller or even 25, 35, fundamentally it gives us more hours of free cooling. What the real challenge we're starting to see with liquid cooling or the chips is we're starting to hit the thermal limitations of the temperature or the junction point on these chips. So there's a lot of discussion going on at the moment is we've been driving temperatures higher and higher. However, have we hit that tipping point where actually at the chip level, we have to start driving temperatures back down again? Now, if we start driving temperatures back down again, therefore it has a flow-on effect to our ability to free cool. Because if we're starting to go down instead of 2030 and above, we start to move back down to say 1525 or 1520, then our ability to free cool is diminished. So there's lots of discussion in the industry at the moment about where that temperature is going, because it will have a significant impact on how we design for cooling. And it has a sustainability impact, because if we no longer can do free cooling or we minimize the amount of hours we can do free cooling, it obviously has a power consumption impact. And last but not least, air cooling is still required. How does air cooling now work with liquid cooling? So liquid cooling, depending on the deployment, anywhere between 10, 15, 20, and as much as 30% is still being air cooled. So you have a hybrid mix between air cooled and liquid cooled. We are still seeing a lot of data centers that are still air cooled because they haven't gone down the liquid path yet. Will the data hall be 100% liquid? Will it still have air cooled? I spoke before about that the underlying compute still very much driven by cloud computing. Will cloud computing sit on high performance compute? There's a lot of talk that it will move towards that because as your Dells, HP, Supermicro, etc., they're moving more and more of their technology to liquid cooling. So we potentially will get to a point where all server technology is liquid cooled. So all computing potentially would be high performance. And once again, that plays into how we are seeing the designs and change in data centers. Just in terms of what's happening from a Schneider perspective, from cooling, we have a long history in terms of cooling. The reason I wanted to show this slide is we've recently acquired a company called Motivair, and Motivair is very much focused on liquid cooling. It's bringing that extra technology and understanding to the Schneider family. And the reason I bring this up is I spoke about grid to chip, chip to chiller, and very much Motivair gives us that insight, what's happening in the chip. And then the chip flows on to what's happening from a liquid cooling perspective. It flows on to what air cooling are we deploying, and it flows on to what chillers. And also, as a parallel activity, whatever's happening at the chip then has a flow-on effect to what's happening at the rack from a PDU, what's happening from a cable connection, what's happening from a bus bar connection. So having that insight of what's happening at the chip level is absolutely critical. So we spoke about the data center, which is the core and the impact it's having on the data center. What we are also starting to see is AI workloads shifting, and potentially those AI workloads are going to move out to the edge. So we're predicting by 2028, as much as 50% of the workload is going to shift out to the edge. So once again, yes, we're going to see a change in the data center, but how is that going to impact what's happening at the edge as well? So we recently used TRA to do a survey to get an understanding here in Australia or the Pacific, what's happening. I'm just going to present a few of these slides. I'll pause for 30 seconds to allow you to have a little bit of a read. Okay, there's a couple of key ones I'd focus in here on. The middle one at the top, 16% and 9% in New Zealand intend to build their own AI solutions. Okay, that's mainly larger enterprises, but what does that look like? Does that mean they're going to build them in co-location data centers? Does that mean they're going to build their own? What does that look like? The other interesting thing is AI spend. 46% of companies are going to spend on AI. And last but not least, 40% strongly agree that AI is being driven by individual employees using work. So 39% also say it is similarly being driven by their leadership teams. The reason I bring this slide up is, yes, we see a lot about AI globally, but this is a survey done here in the Pacific zone. And you can see from this slide, it's key that AI is absolutely being driven by businesses and organisations here in Australia. And then that has a flow-on effect, obviously, the data centres being built here and also what's happening at the edge. It's also reshaping industries. Yes, we're talking about how it's shaping data centers, but AI is going to have a play, and it is having a play in every aspect of our lives. So, from a consulting fraternity perspective, when you're dealing with a manufacturing organization, how is AI impacting that? Retail, education, life sciences, energy and utilities, financial services. It is all intertwined. So when you're designing data centers or the impact for data centers, that then is going to have an impact and a flow on effect to every other aspect of engineering. So current trends, we're seeing AI triggers current environment. So 84% of the research, so they've already invested in AI. So 84% of the businesses we spoke to are investing in AI. And 73% agree with the statement that they will use the same partner they use to support technology initiative to deploy AI. That's an interesting one. So companies are saying whoever's deploying their technology today, they're looking to use that same organization to deploy AI. If we flow that onto the engineering fraternity, so you could argue that, if they're using your organization today to support their developments around technology, they're looking for you to help them with supporting AI. Is that AI compute within a data center? Is that AI compute at the edge as well? And if we look at the broader ecosystem, if we look at mining, we look at retail, we look at electricity, this is just giving a snapshot of where the deployments are. Where are people looking to AI? And as you can see here, is quite diverse. So AI is being used in all aspects of business. And as we flow on to partnerships for success, now, yes, this is talking about Schneider and how we partner with, chip manufacturers, server manufacturers, tech aggregators, and hyperscalers. But in reality, AI is very much a partnership. So when you're working as a consultant fraternity with your customers, it's very much around partnerships. It's working with your customers to around what are they trying to deploy in the data center, what technologies they're deploying, using various vendors, your system integrators, your mechanical, electrical installers. And it's very much around a partnership around deploying this. It's a changing landscape. And if you think about the legacy or the past data centers, if you don't work with your partners or the ecosystem as you move forward to develop data centers, you're potentially going to be left behind. So it's very much around working with your partners. From a Schneider perspective, we're working very much with NVIDIA from a chip perspective, and then our broad ecosystem develop technologies to support the data center. And I had early on the start that is around sustainable business practices. So as we develop data centers and the changing technologies and the impacts that we're seeing from data centers, we still can't forget that we need to align sustainable strategies with business growth, drive power and water efficiencies to decarbonize. So if we look at data centers, are we going to use cooling towers? Are we going to use closed loops? What powertrains? What efficiencies can we gain in the technologies? Decarbonising the supply chain. That equipment that gets to the data center, has it been decarbonised? Low embodied carbon products, whether that's the physical, UPSs, chillers, racks, PDUs, the building itself using low embodied carbon, green steel as an example. Best practices around the building. Can we make the building smaller? And the other one, which is going to become mandatory in Australia, not going to, it is definitely will be mandatory shortly, is reporting to stakeholders. And that's going to be a very interesting one for the fraternity, the consulting fraternity. How do you work with your customers around being compliant in being able to report sustainability aspects of your facility? And that's across the whole spectrum. And data centers will absolutely fall into that area and how they have to report sustainability metrics from a government perspective. And there's a little AI card there. It's just around resources if you're interested in more. And Miguel will be coming up shortly. I'm looking forward to some Q&A towards the end. But thank you for your time. Hope you've enjoyed it. I'm more than happy to answer any of your questions, whether that's today or in the future. So hope you enjoyed. And I'll be handing back over to Miguel to do the presentation with a deep dive into liquid cooling. Thank you.
Thank you, Mark, for your presentation. I'd now like to welcome our second speaker, Miguel Lopez, Offer Manager from Schneider Electric. For the past 6 years, Miguel has been the Pacific Zone Cooling Offer Manager at Schneider Electric and is based at the head office in Macquarie Park. Miguel is acknowledged as a mission-critical precision air conditioner subject matter expert in the Asia Pacific region and excels in helping to develop the future generation of highly experienced mechanical engineering professionals across the consulting fraternity and mechanical contractor fraternity. Wine cellar cooling, MRI, and PET scanner heat rejection to mega-size hyperscale hybrid liquid cooled ready data centers form part of a myriad of application support Miguel provides. Please join me in welcoming Miguel Lopez.
Thank you so much for the introduction. I'd like to go ahead now with the second part of the webinar, which is the cooling architecture in an era of AI disruption. So, as those on this webinar may have seen, NVIDIA have recently launched their AI Factory. So those of you who are familiar with NVIDIA's AI Factory may be familiar with this particular slide, where we're actually pretty much aligned with what's happening in the, let's say, high-performance compute arena when it comes to artificial intelligence. So those that haven't seen the NVIDIA AI Factory presentation, then this essentially is just showing you the fact that all the high-performance compute AI-ready servers are all bundled into racks. So these racks on the left-hand side of the screen are essentially the same form factor that IT managers and so forth have been used to with traditional air conditioning. However, now everything's bundled in, and liquid cooled servers are actually now bundled in with air cooled servers in some instances, or in other instances, these racks comprise full top to bottom liquid cooled high performance compute servers. So regardless if it's a mix of air cooled with liquid cooled servers, the form factor will be a rack, typically 2 meters tall, sometimes 2.5 meters tall. And we do have customers who are looking for that extra high density in their racking. So they're opting for engineered toward a 2.5 meter tall rack. But regardless, that's the form factor which IT managers would be familiar with. Then then these shall be deployed in so-called pods. These pods are rows of racks. Once again, very familiar to those who have experience with air-conditioned racks. Nothing's changed in that form factor. These pods will be typically hot aisle contained, traditionally not cold aisle contained, but hot aisle contained, which yields more efficiency out of any supplementary cooling, such as in-row coolers and cracks. And then across to a building. So the building would be comprising multiple pods. These pods will be then arranged in a particular white space or hall, data hall, which will be supported by outdoor heat rejection. We're going to talk about in the next few slides CDUs, technical loops, facility water loops, etc., which comprise the building. Now, NVIDIA and others who are in the game of AI factories will be looking to deploy campuses. So campuses are multiple of these buildings to be able to give that the ultimate high-performance compute. Yep. So this is the chip which is residing in the rack all the way to the chiller. So this is what I'm going to be covering in the next few slides. Moving across to the next slide. So as part of any kind of responsible equipment manufacturer, and Schneider prides itself has been a responsible equipment supplier to the industry, is to be able to provide that end-to-end cooling to enable sustainable data center growth. So what does this mean? It means empowering the digital transformation and AI transition of our customers by ensuring that critical cooling design and systems are highly available, resilient, and sustainable. So hopefully in the next few slides, I'll be able to convey that message to you. So how does the physical removal of heat look like? So at the moment, there are limitations on traditional air-cooled systems where we're seeing a limit around about 50 kilowatts in one rack. So once again, that's a 2 meter tall rack or 2.5 meter tall rack, one rack alone. So those of you who have an appreciation of what 50 kilowatts or 50,000 watts of power in one rack, you know how awesome and power and heat generation that is. So yeah, there is some mythical applications in air that have gone as high as 60 kilowatts, but that's now pushing the boundaries of what air conditioning is able to do. So as we see in this particular slide, traditionally we have deployed in-row coolers, containment solutions to be able to up the effectivity of the air conditioning to be able to deliver air to our servers. We're reaching a dead end, as it were, at 50 kilowatts. So now the likes of the Dell, Lenovo, other manufacturers are now incorporating so-called liquid-cooled servers, high-performance compute servers, which now their heat density is just now skyrockets in excess of 50 kilowatts per rack. So in the next few slides, we will delve a little bit into that detail, what that looks like. So the next slide is a very good overview of what this architecture, this so-called AI factory is looking like. On the top left-hand corner, you have your precision cooling systems, which those of you with air conditioning for data center background would be familiar with, the so-called CRACs and CRA units. These are perimeter cooling systems that are deployed on the perimeter of your data hall. In the last 10 or so years, the development of so-called front discharge chilled water air handlers or fan walls. So these are the ones that are the flavor of the very large data center designs to the small telco or telecommunication cooling systems. You may have campuses which may have small, let's call it satellite rooms that may require some small bespoke split room air conditioners. Those are available. Bottom left of the quadrant, you see your in-row rack cooling systems. So once again, the reason I'm talking about air conditioning is that these will form of what's called a supplemental cooling for your liquid-cooled system. So as I will explain very shortly, we will still need to be deploying either precision cooling, CRACs, CRAs, fan walls, or in-row coolers. There is an acquisition by Schneider as of late for a company called Motivair, which now opens up the door to so-called rear door heat exchangers. So rear door heat exchangers is a good design to have as part of your mix of equipment to cater for these applications, which we'll be happy to discuss in the next few slides. Moving across, we have liquid cooling. So liquid cooling is essentially now hardware that needs to reside in these facilities, such as the cooling distribution unit. It could be a liquid-to-liquid cooling distribution, or it could be a liquid-to-air. So depending on your server manufacturer's specification or the adoption of the high-performance compute server for your facility, you may have customers that are requiring their server vendors liquid to air. So if there is such a requirement, then Schneider is now positioned to be able to deliver these liquid to air cooling distribution units. But what we're finding in Pacific, Australia, New Zealand, typically is that most customers are looking for liquid to liquid cooling distribution units. So these are, as you can see here, the small rack mounted variety and the megalithic floor mounted variety. The cold plates, we'll talk about that in a minute. These are the ones, the heat rejection plates that go stamped onto the CPU, GPU. And on the far right-hand side is your outdoor heat rejection. So outdoor heat rejection in Australia, in the Pacific zone, typically involves air-cooled chillers. If the design calls for it, we also have the option of incorporating free cooling air-cooled chillers. There are the need for free cooling or not to free cool will be explained in the next few slides. There are also free cooler compressor assisted systems, water cooled chillers, and lastly dry coolers with adiabatic systems to cater for those very high ambience that we have, especially in the center parts of Australia. Temperatures get very, very hot, so adiabatic systems are required. So this essentially forms part of an entire package of cooling in one snapshot for a so-called hybrid data center where you will be requiring traditional air conditioning via CRACs, CRAs, fan walls, or in-rows, and the latest liquid cooling systems to be able to cater for the latest generation AI high-performance compute servers. Moving across. So the message that we want to convey today, and if there's only one thing that you take away from today's webinar, is that liquid cooling is not one piece of equipment, or in Schneider speak, it is not one offer. It is actually an architecture. So it is a, let's call it an engineered system that comprises, as you can see on this slide, a technical cooling system, the TCS, supplementary air conditioning, which I just explained on the previous slide, your liquid cooled racks, your technical cooling system, your TCS water distribution, and your heat rejection. So unlike, let's say, traditional cooling air conditioning systems in the past, we now have the imperative to be able to collaborate and work closely with our IT managers. They are the ones who will be specifying or procuring the high performance compute or AI ready server with, as I mentioned earlier, liquid to air heat rejection needs or liquid to liquid heat rejection needs. All these considerations essentially need to be form part of a survey of sorts, which responsible vendors such as Schneider are very happy to participate in, qualifying and assessing the type of liquid cooling architecture that needs to be deployed at the customer site, whether it's cloud and service provider, very large data centers, to the very small so-called edge deployment where you might have an enterprise that requires one single rack, which needs to be liquid cooled. Okie dokie. Now moving across to some other information with regards to white space, the system backbone being the cooling distribution unit, and some heat rejection details. Let's start with the white space. How to cool servers, the TCS loop with supplementary air. So this is essentially a snapshot of the current technologies in the world of liquid cooling. Let's start from the top, is single phase. So when we say single phase refers to the medium or the fluid that is being recirculated from the cold plate, which is attached to the GPU, CPU, back to the cooling distribution unit. That single phase means that it will be in a liquid phase, and it's the pretty much the favored deployment at this point in time in 2025. There are, however, customers and applications which are requiring so-called two-phase medium or fluid. So two-phase on the bottom of the slide deck refers to a sort of a refrigerant which has the ability to boil as it absorbs the heat of the AI GPU, CPU, allowing that, let's say, gaseous liquid mixture to come back to the cooling distribution unit, which as a matter of fact has a heat exchanger. In its attempt to remove that heat and give it up to the facility water system, it will then condense that gas to a liquid and recirculate the water back to and from the cold plates. So single phase and two phase, in understanding that the fluid is either one or the other, there is a so-called direct-to-chip. Direct-to-chip is essentially delivering that water to, as mentioned earlier, a cold plate or a heat sink that will be heat pasted onto the GPU, CPU, or otherwise on the right hand of this slide deck, a fully immersion type system where the entire motherboard is literally turned 90 degrees and submerged into a tub or a tank of dielectric non-conductive fluid. So once again, this is a bit of a good, let's say, preview of what's available in the market at the moment. Alrighty. So as we saw with the recent announcements by NVIDIA, the heat densities are just pretty much never-ending, rising in a never-ending format. We have to arrive at so-called hybrid data center designs. So these hybrid data center designs, which are in the first instance designed to be air-conditioned for air-conditioned servers, are now seeing a need to have liquid cooling brought into them as a result of the AI revolution. So this is now revealing that direct-to-chip single phase is actually the front runner as far as what I explained in the previous slide, and as far as the medium for these liquid cool systems. So direct-to-chip, single phase. That's not to say that your customer or your particular project or your particular interest could be two-phase and immersive or complete immersion. That's there are customers who are going that path, but the majority that we see in Pacific and globally, as a matter of fact, is direct-to-chip single phase. So just a highlight here to let you know that direct-to-chip is relatively simple. Thanks to its simplicity, it's of adoption. It's the one that seems to be leading today in May 2025. In the next 6, 12, 24 months, who knows who will be the front runner? And the next few slides will explain the reasons why direct-to-chip single phase may or may not be the front runner in going forward. Direct-to-chip technology directly cools the AI chip, as I explained earlier. We have a heat sink that goes pasted directly onto the GPU, CPU. Direct-to-chip technology enables hybrid data center development and does not force the end user to go with 100% liquid cooling. So what this means is essentially a modular type of deployment of your liquid cool system, where direct-to-chip allows for certain high-performance compute servers to be deployed with the liquid cool technology. And there is no reason why you couldn't have, let's say, air-cooled servers in the mix in one server. A little bit complicated, but it can be done. Or have one server or one rack with full liquid cool hardware deployed adjacent to another server, which has air conditioned servers. So let's call them non-AI ready servers. They could be side by side, or they could be segregated into separate rooms. So what we're finding is customers are tending to segregate them where there is a need for co-location to have liquid cooled servers or liquid cooled racks. They are intentionally designing islands of a floor area designated with liquid cooling. But nevertheless, the entire data center is thus labeled a hybrid data center. Hybrid meaning a combination of air-cooled and liquid-cooled servers. Direct-to-chip technology permits a flexible data center design, which we're going to cover in a minute. Uses air efficiently. In other words, we are still requiring the use of air conditioning systems such as CRACs, CRAHs, fan walls, and in-row coolers. And it won't be impacted by the next regulation. So I will be covering the so-called next industry guidance by the likes of ASHRAE. Okay, moving on. So the technical loop is essentially a comprising of one, or in this case, two CDUs, as you can see, flanking a pod of high-performance compute servers. These will typically have the water lines running overhead. So here you can see the red signifying the hot returning water to the CDU, and the blue supply water to the racks. These will be channeled via in-rack manifolds on the bottom left. These in-rack manifolds will be deployed inside the racks, allowing very quick and discrete connections to each of the liquid-cooled servers housed inside each rack. So ASHRAE Technical Committee 9.9 is one that is, at this point in time, actively revising their recommendations for the materials to be used in this deployment. You just cannot use any arbitrary materials to recirculate these fluids, because the orifices of the cold plates that are rejecting the heat from the GPU, CPU are so small that any particulate or any fouling in the water lines has a potential to clog your heat sinks or your cold plates. So therefore, ASHRAE has picked it up and is giving guidance on the materials to be used to convey, in this case, PG25, which is a convention now being established for 25% glycol with some for rust inhibitor and some bacterial inhibitor as well. So lots of activity in the ASHRAE front with Technical Committee 9.9. This is a moving target, so keep those who are interested in following this. Highly recommend that you follow ASHRAE Technical Committee 9.9. Let's move on to the next one. Okay, air-cooled systems with liquid cooling architecture. So, as I explained earlier, the reason we have air conditioning systems that are lumped in with these liquid cool, let's say, hardware technologies is because, as I mentioned earlier, the heatsink or the cold plate is only ever attached to the GPU and CPU. Therefore, it is catering for the heat rejection needs of the GPU, CPU. The remainder of the motherboard, which has a variety of heat-emitting devices, requires some air conditioning to be flowing across that server to be able to remove its heat. So that heat being the residual heat left behind by the let's say, liquid-cooled components on the motherboard can be anywhere between 30 down to 10% of the server loads. This is for traditional servers. When you're cooling switches and storage rooms, these can be as low as 5 to 10%. The cooling of technical rooms, anywhere around 10%. So the message here is that you will be requiring some level of air conditioning, regardless of whether you're deploying tank immersion, chassis immersion, or what is the front runner in the industry at the moment, direct-to-chip cooling. So the next slide is just covering some of the air conditioning architectures that ASHRAE is recommending. So once again, the moving target, ASHRAE Technical Committee 9.9, is recommending the use of the deployment of air conditioning, such as close-coupled rear door heat exchanger. RDHX is the acronym for rear door heat exchanger, or in-row coolers. So this is something that the technical committee is actively recommending as well. Moving along to this, the backbone of chip to chiller architecture, the cooling distribution unit, or otherwise known by the acronym CDU. So it is the one that is transferring the heat. This particular slide, and you will be getting, I'm pretty sure, a copy of this slide deck, shows how the CDU, as you can see on the left-hand side of this slide, is the one that's recirculating the fluid to and from either single phase, as we explained, or two-phase fluids to and from the server. So this CDU then has the opportunity either to reject that heat that it's captured from the server to the air, in which case the cracks, cras, in-rows, etc. will remove the heat. These are so-called liquid to air CDUs. However, the predominant player in the market as of May 2025 is liquid to liquid CDUs. So liquid to liquid CDUs are the ones that will be given up the technical loop to the facility water, and this facility water will then be taken out to some means of outdoor heat rejection, either an existing chilled water loop, or a dry cooler, an open cooling tower, or a dry cooler. So this is a good little explanation of how the hydraulic system works, which you may wish to have a bit of a closer inspection at your leisure. The takeaway message from this slide is that you do have a rack-mounted CDUs, depending on the heat rejection needs of your server, of your rack. A smaller rack-mounted CDU could suffice, but for the larger applications, a floor-standing CDU is probably the way to go. Moving on to the next slide. So what are some of these liquid cooling architectures? So essentially, you have here a graphic of what the CDU is doing. The inbuilt pump of the CDU is essentially recirculating the water to and from the IT equipment. And as you can see there, the returning warm water is then fed through a liquid-to-liquid heat exchanger. That heat exchanger then is removing that heat back to an outdoor heat rejection system. Could be a chiller, a dry cooler, etc. The outdoor system will have its own pump that will be recirculating that fluid. So this is something for the novices in the liquid cooling arena. This is a very good graphic showing how the outdoor system interacts with the CDU and how the CDU interacts with your AI-ready equipment. The little box down the bottom called labeled complementary air cooling is just showing the possibility of sending some of that cool water from the outdoor heat rejection system to some water-cooled CRAHs or water-cooled INROs for that matter. Moving along to the next slide. So the purpose of the CDU, in a nutshell, is to control the temperature to and from the AI-ready servers, to control and accurately deliver the water flow to the servers. Now, your server manufacturer, Dell, HP, and others, will nominate what their range of temperature of the medium or the water coming into their cold plate should be and what the flow rate should be. So these must be, the CDU must be configured to be able to deliver those within those parameters. Water pressure, as you can imagine, recirculating water through a pump. Those with a mechanical background will understand there's a pressure loss as a result of running water through very small apertures which are leading back to the cold plate. So the pump fitted in the CDU must be capable of overcoming all the pressure losses of each individual server, of each individual cold plate. When you have multiple racks, it could be quite challenging to make sure that each server in each rack is delivered with the appropriate water temperature, water flow, and that there's sufficient head pressure for the pump to be able to perform that duty. Fluid treatment over time, whether it's your TCS loop or your facility water loop will require treatment. So there is a need to dose or treat the fluids. So the CDU is the point at which we will be doing the fluid treatment and where we do obviously the heat exchange between the technical loop and the facility water loop. Okay, moving along, as they say, a picture tells 1,000 words. So the following slides are just depicting some of the possible configurations. And in this case, we're talking about water temperatures. So in this case, in the white space, we've got water temperatures back to the CDU of 37 degrees and out to the heat exchanger of 30 degrees. So just bear that one in mind. The temperature difference now on the hot side is 7 Kelvin or 7 degrees. And this is, for example, a 1 megawatt site. For reference, the water supply on the technical loop is 27. On the facility water, it's 20. What we're trying to explain here is what's called the approach temperatures. Our approach temperatures in and out of the CDU of 6 to 7 degrees is essentially not conducive to an efficient design. What responsible equipment vendors such as Schneider are doing is we're pushing the boundaries, and other vendors should do the same, of reducing that approach temperature down to 3 to 4 degrees. So what that means is that your 37 degree water being returned back to the CDU heat exchanger is now yielding 34 degrees to your outdoor heat rejection. So it's up from 30 to 34, which means you can get more energy efficient, many more hours, if necessary, of free cooling out of your outdoor heat rejection system, thanks to those elevated water temperatures. So this will help immensely with your operating expenses and so forth analysis that customers who have like a sustainability type design in mind will definitely appreciate. And last but not least, moving along to the outdoor heat rejection systems. So once again, a picture tells 1,000 words. You will have the opportunity to review these slides in detail when you get a copy of them. And once again, this information is available through the ASHRAE Technical Committee 9.9. But this slide is just showcasing the multiple reference designs. Now, one thing that Schneider is quite good at, all you need to do, jump onto Google, type in Schneider Electric reference designs for liquid cooling systems, and this information will be available to you, showcasing segregated water loops between your CRAHs and air conditioning systems, to having a discrete heat rejection system for your CDU, which is the left-hand side. The middle of your slide here is showing one single outdoor unit catering for both the CDU heat rejection needs and your CRAH air conditioning heat rejection needs. And last but not least, the right-hand side image is showing where you could do a kind of in-series design of your water pipes, where the heat absorbed by your CRAH or your air conditioning unit is then delivered to your CDU. Once again, the design of which reference would be best suited for your project or for your customer's project will be governed by making sure we substitute correct water temperatures, all stemming from the water temperatures that the chip manufacturer is requiring. Will determine the need to backward engineer whether we deploy any one of these three reference designs. Moving along. So going back to the source of truth. So the source of truth with liquid cooling is obviously ASHRAE. ASHRAE is obviously kind of very quickly trying to define and address these design challenges with liquid cooling. So I would urge you to refer to ASHRAE for detail on the following slides. But what I'd like to do now is just show you some of the impact of some of the work that ASHRAE is doing, such as S classification of the fluids on the TCS loop, or the Technology Cooling System loop, and some of the knock-on effects that will have. So ASHRAE at the moment has created so-called S-class classifications for the TCS fluid, ranging from S30 to S50. So you've got S30, S35, S40, 45, and 50. The number is essentially referring to the supply water temperature from 30 to 50, and the facility water loops corresponding water temperatures. Now, once again, going back to the server manufacturer or the chip manufacturer, Dell, Hewlett-Packard, who are adopting chips from NVIDIA and others, they will be designating whether the water temperature should be closer to 50 degrees or as low as 30 degrees. I say that because should you not follow that guidance, then obviously you're avoiding warranties and causing issues with the NVIDIA chip and so forth. And that's something that you don't want the IT managers coming back and challenging your design on. The fact is that up until, what are we in, May 2025, there has been an opportunity to deploy very high S50 water temperature thresholds. An S50 water temperature threshold, as you can imagine, gives an opportunity for large amounts of free cooling hours. So if your outdoor heat rejection, free cooling chiller, or whatever it may be, the fact that you're running 50-degree water on the TCS lip means that you really do not need to run compressors to be able to reject that heat. However, 30-degree water loops means that you will be needing some mechanical cooling to be able to achieve a 30-degree TCS water loop. So just bear that one in mind. 2026, probably 2027, in the next couple of years, we will see, if not earlier, a significant trend towards S50 down to probably S45, S40, even S35 and S30 water temperature thresholds on the TCS lip. And as you can see, the second column from the left shows that whereas we could get away with dry coolers on an S50 TCS water temperature, as we approximate S30, you now need mechanical chillers. So you will need the efficiency, let's say, aspect of running free cooling modes of operation as the water temperature takes a dive, because the NVIDIA chip manufacturers' heat output is so great that we need to now temper that with lower water temperatures, means that you may not be getting the same, let's say, free cooling hours that you were enjoying previously. So how do we capture this trend going forward as mechanical engineers, as designers, as industry professionals? This is the kind of thing we should be talking to our customers. And the trend is this, once again, you can the Technical Committee of ASHRAE 9.9 will show you this graphic showing that the trend, as the heat density of the GPU, CPU, so-called chips increases, the water temperature must come down to be able to reject that heat. So yeah, going forward, what does that mean? That means that single phase systems may not be enough to be able to perform as effectively as two-phase TCS loops. So two-phase, whether it's the TCS loop or the facility water loop, there are some design considerations which the current direct-to-chip single-phase, let's say, architecture of 2025 may need to be tweaked in 2026, 2027. So watch this space, and once again, vendors such as Schneider, in collaboration with NVIDIA, etc., will be working to fine-tune how we should be moving across to different phases, or single or dual phase fluids, etc. Alrighty, so the next few slides is just showing just a recap of what we just covered. I hope this webinar was of interest to you. Just recapping the layout of a traditional AI factory, as NVIDIA likes to call it, where we do have the requirement to be able to develop, as of May 2025, develop so-called hybrid data centers with precision cooling systems, CRACs, CRAHs, fan walls. These have footprints of up to 250 kilowatts for a CRAH, up to 500 kilowatts for a fan wall. The need to deploy in-row cooling systems or rear-door heat exchangers. So all these systems, as part of the evaluation or the qualification phase of your customers, liquid cooling, AI factory, call it high-performance compute facility. These are the discussions we must have to incorporate precision cooling, in-row cooling with your liquid cooling. And as we just saw, thanks to the ASHRAE Technical Committee 9.9, which particular outdoor heat rejection should be deployed as of 2025, and whether we need to be thinking forward to 2026, 2027, knowing that the chiller life cycle ranges anywhere between 10 to 20 years. That should you be future-proofing your liquid cooled system, and how does it harmonize with your precision cooling, in-row cooling systems? These are some of the conundrums that responsible vendors such as Schneider are happy to collaborate with you, are happy to have those roundtable discussions with your customers. And I think that leads me to the end of my slide deck. Yes, it does. So I thank you once again for your time, and I'll hand it over to the moderator. Thank you so much.
Thank you, Miguel. Thank you very much for your presentation today. Well, now it's you, our audience's turn to get involved. So we'll bring our speakers back in, and I think we've got quite a few questions which have been coming through today. So I'm just going to jump straight into those questions. I'm going to ask the first one to direct that one to you, Mark. The question was, does Schneider have plans for big capacity UPS, as we are speaking of 1 to 2 megawatt racks? And then what kind of UPS technology is being designed for this application?
Thanks, Megan. Good question. So I won't go into specifics as to what we're exactly designing, but it's really interesting. We're starting to see limitations around switchboards, so around 5,000 amps. So that also has a flow-on effect to the transformers. So when we're designing UPSs, we're not only looking at, hey, do we make a 3, 4, 5, 6, 7, 8, 10 megawatt UPS? We're actually looking at what is the overall arching design and what are the limitations relating to low voltage switchgear, etc. So that's the key area in terms of the design. Obviously, the impacts of AI and that the power profile of what's happening with the service, we're certainly looking at that and how energy storage is affecting. I could go on for a lot longer, but I'll keep the answer short and sweet. So hopefully that gives a quick answer on that particular question.
Awesome. Thanks, Mark. Miguel, I'll throw the next. Well, I don't know if it's a question, but I'll get you to comment. We've had someone came through with a comment. Data centers consume lots of energy.
Absolutely. Thanks, Megan. So I think industry publications estimate that cooling per se, myself being a mechanical engineer, my forte is cooling, that cooling per se takes up about 40% of the total data center power consumption. So yes, absolutely, they do take, when Mark talks about, a gigawatt and multiple megawatts, this is not only the power consumption, but that consumption leads to inefficiencies or heat that needs to be rejected. So guaranteed, it's unfortunate that, or fortunate to a certain degree, that our lives are becoming more easy as a result of technology, but this technology needs power to be able to be to run. Power generates heat, which needs to be cooled. So hopefully, whoever's interested in having those discussions with myself at Schneider, I'm readily available on LinkedIn, Miguel Lopez at Schneider Electric, to have those discussions as to how big is big, as part of as much as can be said for data centers power consumption, and how to quench that as much as possible with everything we've covered in today's webinar. Megan?
Awesome. Thank you. Mark, we've had a question come through from Illa Moran, and the question was that they were keen to understand the impact of SOCI, S-O-C-I, I hope I pronounced that correctly, Act regulation and data center security. If you could comment upon that for us.
I can. So what does SOCI stand for? First of all, Security of Critical Infrastructure. It's an act that was brought in a few years ago. Fundamentally, if you look at the act, data centers absolutely fall into that. There's an extra piece to that act that talks about advanced security. So what it does in terms of the impact to data centers, by default, because of the act, it's the reporting. So once again, data centers have to report against the act. Very much ties to cybersecurity. So a couple of key aspects of the act and the way it flows onto data centers. One, having very stringent safeguards around the data centers, how you report that, certainly around cybersecurity. So if you do have a breach, how you report that, and in your internal documentation. And as I said, it's a government requirement. So anyone that is going into the data center space, certainly new facilities, going to own or operate, for example, then that act will absolutely play a part in today and tomorrow. And I'm sure the act will become potentially even more stringent as we face more cybersecurity attacks, both on the physical infrastructure and also the IT aspect. So there's the OT aspects of a data center and there's the IT aspects, and both obviously have to be safeguarded. And the Act talks about that and the fact that it's considered critical infrastructure. So that's a quick snapshot on the Act and how it potentially will play within the data center space.
Excellent. Thank you for that. We've got quite a few questions coming through, and we don't have a huge amount of time, so I will try and get to as many as I can, everyone. Ashok had a question for Miguel, and the question was, what are space requirements of CDUs?
Good question. Thanks, Ashok. So, for the so-called edge deployments, Ashok, where you might have a couple of 100 kilowatts in one rack, there is a so-called rack-mounted CDU. This rack-mounted CDU takes anywhere up to 5 U's of space. You mount it at the bottom of the rack, Ashok. So that essentially does not take up any more space than what you would already have in 1 to 300 kilowatt rack. However, we're predicting that to be more of a flavor for the edge type enterprise deployments. However, when you come to the large data centers, the AI factories that NVIDIA is talking about, Ashok, you will need the floor-mounted CDU. And what size is a floor-mounted CDU? It is essentially 1 to 1.5 times the width of a regular 600 millimeter wide rack, and the depth can be as deep as 1.2 to 1.8 meters. Ashok. So, by the looks of it, it looks like a little bit of an oversized rack, but it shouldn't be that much different in height than a standard rack. It'll be about 2 meters tall. So in the overall look and feel, it blends in quite nicely with the rest of the rack. So again, Miguel Lopez, Schneider Electric. Feel free to reach out to me on LinkedIn. Happy to have more discussions, Ashok. Thanks, Megan.
Thank you. Mark, a really interesting question came through around utilising heat. So it was, are there any plans to utilise generated heat like steam generation or in building heating systems leading to a higher energy efficiency?
Yeah, very good question. Depending on how I look at the question, but I'll answer it based on how I think it means. So if you look at data centers, and yes, they're generating heat. So what we have seen certainly in Europe and in colder climates, that rejected heat is being used to heat up water for central heating plants. So in towns, the discussion about having pools next to data centers so you can heat up pools. We've also seen facilities where, like hydroponics, for example, so they're using the heat for growth. So although it's not a direct efficiency gain within the data center, and although data centers are extremely efficient if you compare it to other technologies over the same time frame, using that rejected heat to use it for other sources then overall gives you an increased efficiency of that energy. So yes, there's the energy consumption in the data center, but however, then if you're using that rejected heat for other purposes, and as I said, heating up water, for hydroponics as an example, then there's definitely benefits. But certainly the industry is always looking at how to use that heat and also how do we make the data center more efficient. They're extremely efficient compared to a lot of other technologies over the same time period, as I mentioned. But yeah, once again, that's how I've interpreted that question. If it's not exactly what the question was aimed at, by all means, reach out to me. Happy to have the discussion.
Exactly. Thanks, Mark. We have a question. Can't AI, I like this one, can't AI just design the cooling system for itself? So I'll throw that one to, I think, Miguel.
Yes, of course, AI can design cooling for itself. And the way it does it, just like when you build, for example, an EV car like a Tesla can't just Tesla design the batteries for itself. There are a myriad of technologies that are required to put an EV car together, as there is, in this case, Schneider's expertise is used to cater for AI's need to reject the heat using liquid. So it's by partnering with the likes of NVIDIA, Dell, Hewlett-Packard, partnering with the likes of Schneider and, of course, other respected equipment manufacturers, that we all pool together our resources and design the AI kind of cooling for the chip manufacturer. So, yeah, what's going to happen in the next few years, you'll see this collaboration be a lot more seamless, a lot more, let's say, awkward than it is at this point in time in 2025. It'll be a lot more seamless, and these cooling solutions will pretty much be available and a lot more easier to digest for customers in the years to come. Megan?
Thanks, Miguel. Mark, there was a question that came through from registration. So big thank you for everyone who poses a question when they register for the session today. And this one came through from Charles Brennan from the ACT. And his question was, as AI infrastructure drives up electricity demand, will it outcompete other sectors for power? And is Australia ready for this journey?
Yeah, extremely good question. It's something we discuss a lot here at Schneider Electric around electrification of the grid. Where is power coming from? There's been discussion, obviously, in the recent federal election around nuclear power, whether we should be using that or not. I won't get into that today. But yeah, data centers, give you an idea. If you have a look at what's in the public domain, there's roughly, around 4 gigawatts of data centers being discussed in the public domain. You look at the eastern seaboard of Australia, it's around 30 gigawatts. So, potential there's an extra beyond 10% of extra capacity required on the grid if those data centers get built out over the next 5 years. It's considered critical infrastructure, so will it have a preference over other sources? It may. Once again, that potentially becomes a government discussion or regulators around that. Certainly, as we move to more and more to renewables, majority of data centers in Australia, certainly the large ones, are accessing renewable power, and they're actually putting money into developing solar and wind farms to support that. But absolutely, the question of will we have enough power? Sitting in this presentation and saying it's not a concern or it's not something that should be talked about, I'd be ignorant to say that. So certainly, the industry is looking at it. Governments are starting to look at it. And I think it's an interesting one for governments in general, that the government or the data center sector is a huge benefit to Australia. So I certainly would encourage, the engineering fraternity to be speaking to governments around, how do we support data centers? They bring a lot of benefit. If we just look at the infrastructure itself, that's one thing, but the flow-on effect to data centers and the industry that it drives and the revenue it drives, that becomes a discussion that us, the engineering fraternity, should be having. As I said, I encourage you to have discussions with regulators around the benefits of data centers. Certainly, power, as per the question, it certainly needs to be discussed as well.
Excellent, really good answer. We've probably got time for one or two more questions. Neil, who's watching live, say hello, Neil. What is the design pressure of liquid cooling system? So I think I might throw that one to Miguel.
Cool, not a problem. Thanks. That's a good question, Neil. So what happens, Neil, is we backward engineer from the chip. So what we'll do is we'll actually analyze the quantity of servers with their individual cold plates and the pressure drop associated with each cold plate, be it NVIDIA and all the other competitors in the market. And literally, we'll backward engineer an old-fashioned, if you're a mechanical engineer, you know what I'm referring to, is do a mathematical calculation of all the pressure losses of each individual cold plate, all the pressure losses on all the water lines of the TCS loop, as well as the heat exchanger inside the CDU, and therefore calculate what the pump needs to be. So the pressure for the TCS loop will have to be, of course, the pump that's sized in there. Once again, as I mentioned earlier, one size does not fit all. These are engineered to order solutions. So we will, as a responsible vendor, Neil, will definitely work with you, with your mechanical team, on your next liquid cool project to ensure that all these kind of survey questions are ticked off and that whatever pump, if we're lucky enough to be chosen as the nominated vendor, that the pump in the CDU is sufficient to overcome the pressure losses on your day final system. There are going to be incremental deployments of these liquid cooling systems, day one to day final, and how do we incorporate redundancy, N+1 CDUs, all that kind of thing will be discussed by one of our applications engineers. So we're looking forward to that question and to having that discussion with you. Thanks, Megan.
Awesome, thanks, Miguel. I have a question that I might pose to the two of you, and it's come through from Tim Senko. And it's with the inevitable rise of AI, what can I do as a developing engineer to remain relevant in my field? So I don't know. Miguel, did you want to maybe kick off?
I'll give my point of view from a lowly mechanical engineer. Mark can give it from a high officer in Schneider Electric. But as a mechanical engineer, what I would suggest is talk to your vendors. Hewlett Packard in particular have very good learning opportunities to learn. Dell have the same. Schneider Electric, for our part, we have what's so-called innovation hubs at Macquarie Park in Sydney, in Brisbane office, Melbourne office, Perth office. Contact us. We are not very unfriendly people. We're very friendly people. We'll organize a course for you to come with your fellow engineers. We'll explain the chip to chiller and grid as philosophy to you with all the nuts and bolts. And by having those discussions with vendors such as Schneider, chip manufacturers such as NVIDIA, the people that put the service together such as Dell and Hewlett Packard, and having a continual engagement with all of us, is that you will be better prepared as an engineer to have those roundtable collaboration discussions with your teams back in the office. Mark, is there anything else you want to add?
Yeah, well, I'll take probably a bit more of a broader approach. Yes, there's AI in terms of what its impact it's having, say, high performance compute on the data centers. But if I take it more as a holistic view, AI is impacting every aspect of our lives. So if you looked at my little presentation, I showed, rail, transport, medical, you name it, AI is having impact. So I would encourage, everyone on this call and every engineer to do their own reading. Read about AI, the algorithms, the performance, what it's doing there. Where's AI playing in terms of how it's changing, the new prototypes, what's happening in the space. So yes, the data center, absolutely, as Miguel said, we've got lots of information, lots of things happening there, but there's 7 or 8 different forms of generative AI. Everyone talks about ChatGPT, but it's not the only one. There's lots of webinars and things. So for me, if I look at AI, take a much broader approach, understand how it's impacting various aspects of the world, where it's playing, and using AI as a tool as well. So as an engineering journey, how can I use AI to make myself better? How can I use AI to do a bit of research for me? How can I use AI to develop? So for me, I read lots about AI, and it's not about just my job today. It's about, hang on a minute. It might be a change in career direction because AI is, removing some jobs, but it's creating new ones. So I always say, as engineers, by default, we love to learn. So I would encourage you to learn more broadly than just, hey, focus on Schneider. That'd be great. But hey, just learn in general.
Awesome. That is excellent advice. I think definitely for all of us to keep learning. So look, that's all the time that we have for today. So please join me in once again thanking our speakers, Mark D'Gara and Miguel Lopez, for their time and effort. I would like to thank Engineers Australia's industry partner, Schneider Electric, for their support with the webinar today. Another little side note for all the engineers watching, pleased to share that Engineers Australia's Excellence Awards, the 2025 nominations are now open. So, really help us to recognise the people, the projects that are driving innovation. So you can nominate yourself or a peer or a standout team. And if you just scan that QR code, which is on the screen. My final request is, if you don't mind, please completing the short feedback form, which is linked in the description box below. If you do that, it really does help us to improve and plan our future sessions for you. So finally, thank you again for joining us, and we hope to see you at our next Industry Partners event. Good afternoon.